Hi guys, welcome to your 9-7 notes. By the end of the day, you will be able to choose a linear, quadratic, or exponential model for data. This is important because you can use linear, quadratic, or exponential functions we've been talking about to model any kind of data, any kind of numerical data. So let's do a quick review. When you have a linear function, remember a linear function is one that looks like a line. Lines will always follow this pattern right here, y equals mx plus b. And you can tell if you have a linear function because the difference in the y values is constant. That means the difference in y values, that's your slope. So we have a constant slope right here. It's always going up at that same rate. That makes it linear. Our next kind of function is a quadratic function. We've been talking about these the most recently. Quadratic functions follow the form y equals ax squared plus bx plus c. And here, the difference in their difference is constant. So it's not like a line where you have a slope, and that slope is the same throughout. In fact, this slope changes. It starts out negative, and then gets less negative, and then gets positive, and then even more positive. But the rate at which it's changing, that is constant. So we say the difference of the difference is constant. And then finally, we have exponential functions. Exponential functions follow the form y equals a times b to the xth power. And here, it's not like a line that has a common difference, or even a quadratic that has a common difference in the common difference, but rather exponential functions are getting bigger and bigger at a faster rate and ever increasing faster. But the terms will have a common ratio. So let's go ahead and put that into practice. First, we'll want to decide which kind of model do we want to pick. So what we're going to do is we're going to graph it first. We're going to graph it first. We're going to plot the points, and then we're going to see what does it look most like. Does it look like a linear function? Does it look like a quadratic function? Or does it look like an exponential function? So let's plot them. For A, we have the point 0, 0, and then 1, 1. Now right now, to me, that looks like a line. That looks like this line right here. Let's keep going and add more points and see how it goes. We have negative 1, negative half. Shoot, that doesn't lie on our line. Well, and one more, over 2 up 3. That doesn't lie in our line either. So this is not linear. This guy, in fact, is going to be exponential because it fits an exponential function the best. So we'll call this guy exponential. Go ahead and do exercise B. Plot the points and see which model is most appropriate. All right, let's go ahead and do exercise B. So we plot negative 2 up 11, over negative 1 up 5, over 0 up 3, and over 1 up 5. So this is not linear. Oh shoot, I missed my point here. These points should be over 1, 5, like that. Now, it looks a little bit linear, but not quite, because it starts to go back up again. Because it goes back up again, this is going to be quadratic, because it's forming a U shape like a parabola. So this guy looks like a quadratic function. So to choose a model by graphing, first plot the points, and then see what fits. Now that's great, and these models look like they fit our data, but how can we check this algebraically? How can we use algebra to check it? Wow, that was such a good question. Who asked that question? Matt? Good job, Matt. That was such a great question. Way to go. Well, let's find out, shall we? All right. So, here our example is going to be how to choose a model using differences or ratios. This is going to be our algebraic way. So what we're going to do is we are going to put all of our points into an XY table. Oh, good job. We already did that. And then we're going to find out their common difference. Now, I know you have a question, and it's, what is that common difference? Well, Judah, thanks for asking. That's a great question. The common difference is the difference between the y's. So to get here, we add a half. How do we get from here to here? Oh, good job, Hannah. We add 1. And how do we get from here to here? Oh, good job, Ian. We add 2. So our differences in our y values are not common. Shoot. Well, we can check differences again. We can see, do those differences have a common difference? Well, let's find out, shall we? All right, so we're going to call this not our first common difference. We'll call this our second common difference. What's the difference between a half and 1? Oh, good job, Mia. That's a half. And what's the difference between 1 and 2? You're right, Miguel. That is 1. Guys, the second common difference is not common either. So that's not going to work. Sorry. So maybe instead of finding a common difference of our common difference, maybe we try to find a ratio. Do you think we can find a ratio? I hope so. All right. So now we're going to try to find a common ratio. What is the rate? Well, first of all, what does it mean to be a ratio? Dougie, you're so right. A ratio is when you have a fraction. You have something divided by another number. Okay, so who can tell me what is the ratio from 1 to 0.5? We're going to find that by doing 1 divided by 0.5. Oh, good job, Will. That is 2. Next, to find the ratio of 2 over 1, what is that equal to? Oh, Sydney, you're so right. That is also 2. Way to go, guys. So we have a common ratio. What is our common ratio here? Catherine, you're totally right. Our common ratio here is 2. Awesome. Now, because we have a common ratio, you see up here, a common ratio fits our description of exponential functions. So this is going to be an exponential model. Awesome. Let's plot, or not plot, let's put our activity B. Let's put these into a table. Oh, hey, look. It's already there. So, what is our first step going to be? Thanks, Ty. Our first step is going to be to find a common difference. Way to go. So what is the common difference here? How do we get from 11 to 5? Oh, Stephen, you're so right. That's minus 6. Awesome. All right, next. What is the difference here? Ah, good job, Tony. That's minus 2. And lastly, what is the difference here? Ah, Ryder, you're totally right. That is plus 2. Now, guys, is this common? Are these differences the same? Thank you, Ariana. They are not the same. So, let's try again. Let's try to find our second common difference. What is the difference here from -6 to -2? Oh, you add 4. Good job, Lizzie. Now, how do you get here from -2 to +2? Thank you, Brayden. We add 4. Now, guys, is this a common ratio, or not a common ratio? Is this a common difference? It is. It is the same the whole time. We have +4 and +4. So even though our common difference was not, in fact, common, it was not the same. What about our second common difference? That was the same. Excellent. So when we have a second common difference, that's the difference of the difference, that's going to make this quadratic. Awesome. So this is a quadratic model. Should put my answers in boxes, huh? Super. Now Riley just pointed out an excellent idea. Riley noticed that our plots, our points, are the same. That from example 1 to example 2, I used the same set of points. I used the same data for each type. Isn't that great? So it doesn't matter what method you use, if you graph them, or if you find common differences or common ratios, you will still get the same answer. These points are an exponential model, and these same points are still an exponential model. These points, however, when we graph them, we found it looks like a quadratic. And when we looked for common differences, we found, oh, this is still going to be quadratic. So it doesn't matter which way you use, you will get the same answer. And that's why we like math. All right. Who can tell me about parent functions? A parent function is, thanks Jake, you're totally right. A parent function is the most simple function in a family of functions. We're going to want to use a parent function to write our model. So let's recap all of our ideas, and then we will write a model for a real life situation. So if we put our data in our table, or if we put our data in a graph, and we see that they have a common difference will tell us that that is linear. Now, Jake, can you tell me what function follows, what do linear functions look like? Linear functions, Jake, you're so right, are y equals mx plus b. I forgot to add that the parent function is just a plain old y equals x. Now, if we have a second common difference, so if our common difference didn't work, and we need to try out a second common difference, what is that going to be? Ah, Tracy, good idea. That will be a quadratic. Now, Rachel, can you tell me what is the standard form of a quadratic formula of a quadratic function? Way to go, Rachel. You're totally right. Y equals ax squared plus bx plus c. And the parent function of quadratics is y equals x squared. Now we have one more kind of model type that we're talking about today. Chenny, what is it? It is exponential. Way to go, Chenny. So we know we have an exponential function if the difference of our y terms is a common ratio. Now, Amanda, what do all exponential functions look like? They all look like y equals a times b to the x power plus c. Now, the parent function, this is actually kind of a trick question. There is no parent function. It would have to be y equals any number, so like 2 to the x, but it doesn't have to be 2. It could be y equals 5 to the x, y equals 8 to the x, y equals 1/2 to the x. That kind of deal. All right. Now let's put this as a visual. So how to tell what the data show, you're going to want to make an XY table. So you're going to put all your X's on one side, you're going to put all your Y's here, make your XY table, and then start by finding a common difference. If you find a common difference, awesome, that's linear. But if you don't have one, then try to do one of two things. Either try to find a second common difference, but if that doesn't work out either, then you're going to go back a step and you take the common differences that you found and you see if they have a common ratio. So we're going to do that one last step to model our real world data. Please also notice we did do this earlier. So we started out in example 2 by trying to find a common difference. It was not the same. So we tried to find a second common difference. That was not the same, but then we found a common ratio, and that was the same, so it's exponential. In part B, we started out by trying to find a common difference. That was not consistent. So then we found a second common difference. We said, oh yeah, the difference between those differences, that's the same. So that's going to be quadratic. Let's do one more. So our wonderful theater company here at Whittier Christian made a table of their annual income. How much money do they make every year? What type of function best models the data? And then we're going to write an equation to model that data. So first, let's graph it. So at year 0, we have 18,254. It's going to be about here. Then we have 18,730, just like there. We have 19,215, which is like here. 19,695, which is what, like there. And then 2175, which is about here. Now just looking at it, what do you guys think? Yep, it's linear. Way to go. This looks to be linear. But maybe it's not. Maybe it's just like a really, really wide parabola. Or maybe it's like a slow exponential. Let's find out by using our algebra skills. So we know if it appears to be linear, we want to find a common difference. So we're going to test for a common difference. We're going to do that by looking for the differences in their y values. If these are x's, look at our y's. What is the difference here? That's 476. What's the difference here? That's 485. What's the difference here? Well, 19,695 minus 19,215 is 480. And one last time. Oh, hey, it's 480 again. That's cool. Now, guys, is this common difference common? Is it the same each time? It's not. But guess what, guys? It's close enough. Because this is real life data, and real life does not match math perfectly all the time. I know, it's so heartbreaking. But this is close enough to a same kind of constant difference. So we are going to go with linear. Yay. Okay. So we want to write a model. That's our whole problem here. What does a linear model look like? We'll want to use the form y equals mx plus b. Remember, m is our slope or our rate of change, and b is our y-intercept. Looking at either our table or our graph right now, can you find that y-intercept? It's right here. Our y-intercept is where x equals 0. So we already know that our y-intercept is 18,254. So all we have to do is find the slope. Nice. What is the formula for slope? Remember that slope is rise over run. So that's going to be your change in y, or y2 minus y1, over your change in x, x2 minus x1. Now guys, we have a lot of options here. We could pick like the average of all of these common differences. We could say, hey, you know what, let's just find the difference from 4 to 0. That'll give us a nice average. There are a bunch of ways. I'm actually going to do the later one. So I'm going to find the slope from here back to here. Okay. So let's go ahead and plug those values in. That will give us our second y is 2175 minus our first y, 18,254, divided by our differences in x. 4 minus 0, which will be 4. And once we calculate that all out, guys, that comes out to 480.25. Now that should make sense because these are all kind of around 480-ish, so we would expect their average to be around 480-ish. Awesome. So our model, we're going to put it all together, is y equals 480.25 times x plus 18,254. Fantastic. We did it, guys. That's our model. Way to go. Because our model citizens. Now let's test it. A good mathematician always checks his or her work. So we're going to pick 2 points and we're going to plug them back into our model and see how they work. We can pick any one of these points from our table. We don't want to use 0 because it's got our y-intercept, so we know that'll work. So let's pick 2 of these points and see if they're close enough. Which ones do you want to pick? Thanks. Number 1 and number 3. Awesome. If you want to test up point 2 and point 4, go for it and check back with me. We'll see how close we are. So to check point 1, that said that after 1 year, they earned 18,730. We'll plug that in and see if it works. Okay, so we're going to plug in for our x, we have 1, and for our y, we have 18,730. So let's plug those into our model and see how close we are. So by plugging in y, we get 18,730 equals 480.25 times 1. That's going to be nice. Do you see why I picked that one? Good job, me. Plus 18,254. And that will come out to be 18,734.25. Now, that's close. That's close to 18,730. And that's close enough. Close enough. It works. Cool. Let's try point 3. What was point 3? That was after 3 years, they had 19,695. Let's go ahead and plug that into our formula. See how that works. So our y value is 19,695 and our x value is 3. So we have 19,695 equals 480.25 times 3 plus 18,254. Now on the right is equal to 19,694.75. And guys, what do you think? Is that close enough to 19,695? Yeah, that's 25 cents away. That's amazing. That's definitely close enough. Way to go. Super. So in sum, we are going to use this guy right here as our key idea. If you have a bunch of XY points, put them on your table, Find if they have a common difference. If they do, it's linear. If they don't, see if those common differences have a common difference. If they do, it's quadratic. If not, see if our original common differences have a common ratio. If they do, it's exponential. Amazing. Remember, you can always graph it to see if it looks right, and have a wonderful time on your homework.